Hello, 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 and good afternoon. I hope you have done with your lunch and you are feeling good and you're ready to learn something new. Most of the things about me has already been presented. So my name is Oleh. I'm from Kyiv, from Ukraine. My main focus is reactive programming, reactive system. I've done lots of contribution to different libraries in that sphere, especially in Java. But I'm curious how many software like reactive engineers or people who tried reactive programming, reactive streams, or Reactor or RxJava I have here. Like, oh, okay, that's good. Then this talk is for you because today we're going to talk about network protocol, about reactive network protocol, about cloud, microservices, so please expect that. Okay, today's outline. We're going to start with the problems that we would like to solve today. Then we are going to look at RSocket and we will try to play a little bit with RSocket. That's our main outline. Is it good for you? All right, let's start. So let's start with the history of building network in general. Everything started in the 19s when we just created computer and decided to gather them together over the network. At this period of time, we had like a different network protocols. We created AOL, IPX, SPX, and most probably you have never heard about those protocols because they are proprietary protocols. We got one open source, open protocol like TCP, which was the best solution, and all this proprietary protocol went into the history. The next cycle or iteration in the development was 2000s. So this period of time, we started building service-oriented applications, so the time of building services. And this period of time, we developed Corba, COM, DOM, or DCOM, and HTTP. And of course, all these proprietary protocols from Microsoft, from Oracle, from different companies went into the history again and were totally eclipsed by HTTP. That's what was the main protocol for building services starting from 2000. Then it's a little bit opinioned. In 2010s, our applications started growing. We started building web application, and for that purpose, in order to build proper API, like the highest level of OSI model, we started creating some architectural solution like ASB, SOAP, XML, RPC, and REST. And it's obvious that the REST was the best solution, of course, if you are not in the bloody enterprise, but in any case, they went into the history and nobody uses them today. And finally, we got to today's, 2020 almost. And today we have like HTTP, more modern HTTP 2. We are about to get HTTP 3, and everyone almost using RPC over gRPC. So the main question is whether those technologies fit today's needs. But in order to figure out that, we have to probably ask the question, what do we have today? What kind of applications we are building today? So let's take a look and answer that question. Basically, today we are building microservices. How many of you are building microservices today? Just for statistic. All right, almost 90%. And basically, more wider statistics says that 90% of the companies are using or planning to use microservices today. All of those companies started to move in their applications from bare metal, from own data center to cloud data center, or to cloud platforms. Amazon, GCP, that's what we are adopting today. And finally, 99, almost everyone experienced problem with building microservices. So the next question should be, what do we need today from communication, from protocol perspective in order to solve our problem? So the question is, what problem do we have to solve probably? So let's take a look what today's microservices needs. First of all, we are not sending bytes today, right? We are not sending bytes. We are sending logical messages. We are sending JSONs, protobuf, whatever message format we have, but we send real messages. And of course, protocol under the hood could be binary, but it should be message-oriented, which means we don't have to deal with bytes at all. We don't have to manually count in and figure it out where is the beginning on the end or the end of the message through the stream of bytes. No, we don't have to do that. That should be provided by the protocol. So yeah, we have to send message, decode it to binary format, and then receive the whole payload and decode it back. So where is the gaps here? First of all, layer 4 protocol in OSI model like TCP, UDP, Aeron, Quick does not provide that that kind of messaging. They provide really low-level access to byte streaming, and so forth and so on. Of course, some of them has like framing, but the main case is, and the main problem, that frames sometimes is not equal to messages. Sometimes real message is much bigger than just one frame. It could outsize the one frame, and we can take a couple of them. And then we have to solve problems like, okay, we want to have headers like metadata. We want to have like our data separately. And this is the whole message that should be like sent over the network. So should we solve that? And of course, those protocol doesn't solve it. Of course, we have like HTTP or similar protocols, like higher level protocols which provide that. But let's move forward. Let's talk a little bit about performance. So performance is critical characteristic today. Why? Basically because everything is run in the cloud, and the more performant your applications are, the less CPU you spend on your calculation, the less time you spend on network, and so forth and so on, the cheaper cloud is for your business. You don't have to run 1,000, you can run just 100 of servers in order to serve your users. And of course, one of the techniques is multiplex all the data through one connection. That's from protocol perspective. So what we want to have, we have like stream IDs, like logical stream inside inside the single connection, and then multiplex all the messages through it. That's what we want to have. Where's the gaps here? First of all, like again, low-level protocols like TCP, UDP does not provide that. You have to add that yourself. Then HTTP1, HTTP1.1 uses more than one connection. HTTP1 uses connection per request, which is absolutely inefficient. It was upgraded with HTTP 1.1, but you still use a couple of connections, and you have to pipe in your request, but sometimes it's not the best case. And of course, it was solved by HTTP2, but let's look at the communication. From the communication perspective, what happens with our protocols, and what do we need probably? So first of all, we need request response. This is most common pattern for communication and for doing like data sending forth and back today. But we are moving into the future. So along with that, we need some real-time or streaming data sending. So probably we have to have server-side streaming or client-side streaming or bidirectional streaming. And that's not it. That's not the only cases. A part of that, we need peer-to-peer communication. So basically, we need client and server, but only just at the very beginning in order to establish the connection. But afterwards, we want to have them as peers, like as equivalent responder or requester. And then both of them should be able to send a request and receive a response. And yeah, no limitation at all. So where we have gaps again here? In yesterday's protocol, let's call it. Again, in TCP and layer 4 protocols, we have to define all this semantic ourselves. HTTP1, HTTP 1.1, HTTP 2 is not peer-to-peer, and even is not bidirectional protocols. And yeah, you probably heard about something like call it server-side push, but you have to look at Spec first. Spec says that from communication and from semantic perspective, it's still request response. And in order to get push from the server, you have to make a request. That's the main problem. That means that nothing has changed from the protocol implementation. Just some improvements, but no communication and no semantic improvements. And finally, STOM MQP protocol support pops up. It's better, but you have to define like request response yourself. Okay, and almost finally, I'm not saying that this is the last thing, resilience. Today we are building distributed system. Today we're building cloud-native application which runs in on many instances, the same app in like different copies. And we have to preserve stability of our services. So first, one thing that we want to have at our application is flow control. So which basically means that we have receiver, data receiver or message receiver. And this receiver should somehow control the pressure of data from producer side. Because if we're not going to control that, we will be overwhelmed and our application is going to crash. A part of that, we have to do proper resource control or resource management, which means that we have to apply techniques something like rate limiting, circuit breaker in order to avoid cascade failure. We have to limit like to say we are not able to receive million of simultaneous requests. We want to have just 100 of them. So please send not more than this number. And we have to have something like monitoring, tracing, and in order to have a good debugging. So where are gaps here again? Most of protocols like gRPC relies on binary or byte flow control from underlying protocol like HTTP2 or TCP or any other protocol. But the problem here is that your messages is not equal to your byte. Every message is different in size, and basically what happens to your application is something like that. You're opening your tape in order to get a stream of water, but the pressure is too high from the sender side, so all the data or all the water is just throwing into your face. And then you close it and say, all right, what's happened? Let me try to collect all the data into my glass, for example, because glass could be your message. And then you open again and the same happens. So this is how flow control works on the byte level or TCP or HTTP2 level. And probably what you want to have is something like this. You want a logical flow control, logical message flow control. You want to say, okay, you want to have 10 bottles of water, and then you want to drink a little bit as you want and process all the water as fast as you can. So that's what you want to have. And of course, there is some solution from message sending on message-oriented protocols like MQP or ZeroMQ. You can send a message and then receive an acknowledgement, but it's really slow. It's like collecting your all data by drops, like one drop, another drop, and so forth and so on. So it's not efficient. And most probably, a part of that, you want to apply some technique like rate limiting, circuit breaking in order to avoid like this stream of water from TCP. But then like all these techniques are predictive, they are proactive. They're trying to figure out whether you are good or not. So you can imagine that you are not good. But someone periodically tries to open this tape with stream of water and check, are you fine? And now? And now? And you all the time receive this stream of water spontaneously, and you probably won't be able to recover from that state. And finally, like all these libraries, like all this technique, like rate limiting, circuit breaker, monitoring, tracing are external. The protocols were developed at the point where nothing was about that at all. And afterwards, those technologies appears, and you have to have external libraries, and you have to integrate them, and so forth and so on. So this is another gap. And of course, we have to have the support of all these protocols like HTTP2, HTTP1, and so forth and so on, everywhere, including browser, mobile, and embedded. And the problem here is, like, for example, HTTP2 does not have proper, like, low-level access from the browser side, which means the only thing you have is your fetch client or XML or how this client in JavaScript, in browser of JavaScript works or called, and you have to send request response, and it's still non-efficient. And yeah, quick HTTP3, which should expand that possibilities, are not that here, and we have to live somehow in mobile and embedded because all of those protocols were developed in the era where this wasn't important. So, part of that, we have to build our API and how to solve routing, how to define MIME types. Some protocols provide that, some not. We have to solve it as well. All right, we're at the era of today, and what we can understand is that we are at the cloud-native and microservices era, right? And the question is whether those technology could fit and could solve. Now we saw that none all of them can solve everything at the same moment. So probably they're going to go into the history, and we have to ask a question, what next? So from my point of view, next should be RSocket. You may wonder what RSocket is, or what I'm talking about at all. So RSocket is basically a protocol developed by leaders of cloud-native and real huge distributed system developers. Like it was developed at the very beginning at Netflix. You know, Netflix is a huge shop of microservices, and they know how to build it, and they know what they need. And from protocol perspective, RSocket is layer 5 and layer 6, so it's a layer of application protocols. It follows Reactive Stream Semantic, so it's implementation of Reactive Stream specification as a network protocol. So basically, you can take your Java or RxJava or Project Reactor and transparently, without losing the semantic, send this like flow or mono over the network, so your recipient will get the same fax and the same mono with the same behaviors and will be able to communicate in the same manner, but over the network. Isn't that cool? Part of that, it has application flow control, logical elements flow control from reactive streams, and it supports RPC and event-based communication, but we are going to talk about that a little bit further. The most important that this protocol is really fast. It's 10 times faster than HTTP1. I'm talking about HTTP1 because it's not a single connection based, and it's really fast and really utilize well your CPU and your computers. So you should consider them. It's not slower than gRPC, it's the same speed, but it provides much better resilience. So let's talk a little bit about features of RSocket. First of all, it has binary messaging, which means that if you want to send your, for example, ghost over the network, you have to convert this ghost or decode your ghost into, or encode your ghost into binary format. Then you send it, and RSocket takes care of delivering the whole payload. You don't have to worry about that. So you will be able to encode it or decode it back to your logical message. From internals, you have logical message. It provides a defined metadata and data. And all of the things are binary, so you can put anything with any size into your data payload, and you can specify any metadata. And moreover, protocol solves something like tracing, like monitoring, like routing out of the hood, so you have something like composite metadata or metadata extension, which allows you to define your routing or routing for this specific message. It allows you to define your MIPE type of this message, so every message possibly could be with different format or different type of encoder and decoder. And and you have this out of the box. What else? What about performance? From the performance perspective, it follows the same technique as HTTP2, as HTTP3. It allows you to multiplex all your logical stream. It defines under the hood all the identification for every message and to which stream it relates. And only thing you have to use, for example, is project reactor from the Java perspective or from the application perspective. So basically, send your reactive streams and that's it. The library, the protocol will do everything for you to deliver your messaging in the same orders within the one connection. Isn't that cool? What else? You have to think, okay, so it provides some framing, some logical stream identification, some infrastructure, but should it be related to transport? No, it shouldn't. It just defines your framing and that's it. Some additional feature on top of something existing. And you can easily change any underlying transports. So for example, you can use WebSocket, and WebSocket defines something like frame size, so you can follow that, or it's not necessary to use it, or you can use TCP, and then we are going to add some frame size and so forth and so on, or you can use Quick, or you can use Aeron. There is no limitation. You don't have to change your logic. The only thing is just change your transport, and the semantic and the framing will be the same because it's defined by protocol. Resilience. As I said, we have reactive streams back pressure. So it means that if you're going to request, for example, 10 elements or 11 elements, this request, this method invocation will be encoded to binary frame, will be sent over the network, and your recipient, like publisher, will be able to decode it back to your number, to method invocation, and produce exactly the number of message you need, and not more. And it's much better, because in TCP you just send data, you send binary stream into your window, which basically a representation of buffer. And your network card here and there should keep this data until an acknowledgement. And only after that you will be able to send another portion of data. But this is proactive. In this case, we really reactively wait for requests from subscriber. We ensure that subscriber is ready, and only afterwards we start sending something. Okay, from another case, from another perspective, I've been talking about circuit breaker and rate limiting. These things are built into the protocol. You don't have to use them at all. It's built into the protocol. There is something called leasing. Leasing is basically a way to control everything from the responder side. For example, you have client and server. And server got one connection, another connections. And you have then on the client side, that was before. On the client side, you would implement some logic for keeping the rate of messages for requests and so forth and so on. And then you have to manage that somehow in distributed way. No, you don't have to do that all with RSocket. What RSocket provides you server knows its capacity. It knows how many requests per second it's capable to receive at this point in time. So it can say to all the connections that you body have like 5 requests per second for the next 5 seconds. And you body have like 10 requests per second for the next 5 seconds. And you have another number. So it can share its capacity between all the connections. And in case something went wrong, for example, you don't receive any leases from the server side. It directly means that you don't have to call it. You are not allowed to do that from the protocol perspective, and you probably have to choose another instance to send, which gave you some more leases than this one. And you don't have implement rate limiting because it's naturally built in. Yeah, this is a little bit complex, but yeah, I will be able to answer more about that afterwards. And about communication. RSocket not only about streaming. It provides everything we need in order to build cloud-native application. For example, request-response communication pattern or request stream, you're able to send request and receive stream of messages. Or request channel, which is basically stream. So you can solve that with that client-side streaming problem or bidirectional problem, and you don't have to do anything in addition to provide this communication pattern. And the most important, not that most important, like we have fire and forget, it's a little bit more tuned at request response, like you can send and forget about that. But the most important that it supports peer-to-peer communication. Only at the beginning, client have to establish connection. Then you have real peer-to-peer. Both of the sides can implement or expose some API, and then the server can ask for something from its perspective, as well as client can ask for something to server. That's real peer-to-peer communication. So let me show a little bit some code really quickly, because we don't have that much time. But I want to show you something really important that you remember. So we are going to look at RSocket Java and RSocket JS from the browser perspective, so you will feel this real peer-to-peer communication and all these features. So in order to start using RSocket, there is 2 types. So there is RSocket, which is basically representation of your API, or at the same time, it could be a client. And it provides all these methods that I just mentioned, like request stream, request channel, and so forth and so on. The representation of data in RSocket world is payload. So payload is something I mentioned. It's your local message. It's your logical message. And it provides your data. In Java, we have good integration with Netty, so you can achieve something like 0 copying and really high performance, as well as we have metadata. So all these features are built in. Then in order to start using RSocket, you have to, for example, to define your server, you have to say RSocket factory, receiver, and then you have a builder with lots of features. And you easily can define like what behaviors, 0 copying or something else. For example, there is something called resumability. The protocol was developed with the sort of mobile and embedded devices. So you can imagine your mobile devices could easily went out of the network, and then you have to reconnect, and then somehow you have to continue streaming. And this is something you have to solve with all this protocol that you got yesterday. With RSocket, you have something called resumability. This is part of the protocol. And you can easily resume your logical streams, which were sent to your client from the point of disruption of the network. You don't have to implement anything. It's built in. You can specify the storage, like you can specify small storage in memory or cold storage in case of something. You can specify session for your resumability, but all these features are built in. Or you can control leasing, as I said. Yeah, there is leasing. So a part of that, what you have to do, you have to define a scepter. So a scepter is new socket, a scepter is a scepter for your connection, for incoming connection. And it provides you something like connection payload, which basically gives you a chance to verify who is connected and whether it's allowed to, this client allowed to do something with you. And you receive a representation of your connected client. So you basically can use this RSocket in order to make outbound calls. So let me quickly skip all the things. Yeah. One more thing, you can, as I said, specify really easily the transport. So you can choose TCP server transport and define like it on some port, or you can use WebSocket transport. It's really it provides really good API, and from protocol perspective, it does not limit you. So you don't have to use only a single solution like with gRPC, I mean HTTP2 for gRPC, but you can easily switch any transport you want or implement something yourself. So let me quickly go back to what was before in order to show you all the super cool features of RSocket, and this could be the implementation you want. So you override it, you return your API, you return request stream, and you return your flux of payloads. That's what you should do, basically. And you can create it, and nothing special here. So if you're going to run it, we will see that it's running. One more text. And yeah, it's running. And it's running on port 8080. And here I have some JavaScript client, which looks similarly. So what I have to do is RSocket client, specify transport, specify data encoder, decoder, specify MIME type, and I can use some featured extension or message composite metadata for my MIME type in order to tell my server that this is composite metadata. And then once I connect it, I receive RSocket, the same RSocket as for Java, and I can call request stream, request something, and so forth and so on. So let me just open the browser. It's running on the port localhost 1, and I have to open my my console, and you can see that I got a connection, and nothing happens. So this is something unexpected, basically. What's wrong? I requested 5 messages. So let me look what's going on in the stream. All right, probably something went wrong, as usual. But nevertheless, that's fine. Let's try to reestablish connection. No, it doesn't work. That's fine, demo effect. I don't have like much time, but the takeaway points is that the API good, developer experience is good, or should be, not at the demo stage, but we can talk about that afterwards. So let me go back to my slides and quickly finish all the things. What you have to remember about RSocket. RSocket provides a really good development experience. There is a couple of clients for different languages. It allows you to use any development API or architecture style like RPCs with gRPC or messaging, any format, and the most important, any transport. You are not stick with some specific one. So more things. There is RSocket RPC. It allows you to replace gRPC at all. It provides the same code generation things as it done with gRPC and protobuf. And there is Spring Boot Starter RSocket, for example. I'm Java developer, I'm Spring developer, so it's something important for me, and I can use Spring messaging with integration of RSocket. All right, a little bit about important things from developer perspective as well. What about cons? What about disadvantages of RSocket? So this is pretty new and bright technology, which means no huge adoption. A part of that is still under development. There is lacks of good documentation, and there is lacks of implementation in languages such as Swift, Python, or Rust, for example. But what about prawns? Cloud-native protocol, designed for high performance, has really good resilience with reactive streams. And the most important, we are expanding our audience. We just created Reactive Streams Foundation, and RSocket is the first project here. So we expect the growth of the usage of RSocket pretty soon. What next? Let's talk a little bit about the future and the real enterprise. So before this moment, we had something like this. We got one computer connected over network, over TCP with a router, which sends our connection to another, and so on and so on. And finally, we got our request or connection at another computer. Just imagine that we are going a little bit higher. What if we're going to abstract all these things with RSocket? And instead of computers, we're going to communicate over services. And instead of routers, we're going to have something like RSocket broker, which will route our connection to another service, and so forth and so on. And all this communication will be done over the RSocket as a network protocol. That could be something interesting, but this is another talk, and we don't have enough time for that. So takeaways for you. Most of yesterday's protocols has gaps, and it was clear. RSocket covers almost all the cloud-native and microservices cases and problems. But we're still developing and improving the protocol. And if you want to help us, we are welcome to get your contribution, by the way. Community is growing. And even today, you can build really full-fledged, high-performance cloud-native application with RSocket. So what to do next? What to read? We have RSocket.io. This is official web page. We have some video channel where we gathered all the videos so you can learn more. We have community forum, so you can ask any question related to RSocket, and you're more than welcome. And you can follow me, ask question directly at the Twitter, and I'm more than happy to answer them. That's basically it. And if you have something to ask me, just go ahead. Thank you for your attention and for being there.
So we are somewhat out of time, but there are a couple of questions, and I think that fortunately you managed to answer them after they were asked. So I think that biggest downside you already mentioned. Do you have a roadmap? When do you plan to release version 1.0?
So basically, at protocol version 1.1, we want to implement we are about to release the first version of protocol itself, but we are still discussing something like metadata extension. We still need to cover all the cases for metadata and meta information sending. The part of routing and the part related to Leasing. We're still doing some discussion in order to make sure we solve all the resilient cases, and once you start using it, you will be able to solve all your today's problem. That's like brief roadmap for RSocket. Once it happens, it's going to happen maybe in a month or two. You will get the first release of RSocket. That's the plan.
Fantastic. Thank you.
Thank you. And if you got more questions, I am here still.